Fiat lux. You know it? We should have a Latin class too. That means let there be light. Okay, physics time. The objective is model the relationship between x and y components of projectile motion. And so the physics concept of this lesson is projectile motion, but that's not really what we're going to focus on for much of the time. I am trusting that you remember projectile motion in general from physical science, but we're going to spend most of our time talking about the math, the relationship between the x and y components of projectile motion, in so much as we are also going to learn about how to do the upper level math for this class, which is called trigonometry. And we're going to do it pretty basically at first, but as we get more and more involved in especially the next chapter, we're going to get a little bit deeper into the trigonometry. So projectile motion. Projectile motion is the motion of an object, which is influenced spelled correctly, by gravity, and may have a horizontal component of motion. A basic piece of understanding you should have for this lesson is this. What have I drawn? Can you guess? It's about math. Yeah, it's a quarter of the, in fact, it's the first quadrant of the
graph.
Yeah, what's this called? Let's start with this. What's this little point here called? Because I think that'll make sure that. Yeah, what's this little dot right here called? Which indicates usually 0. It may or may not, but usually 0. What is that little point called? The
Axis.
No. Origin. This is the origin of the Cartesian coordinate grid. You remember this from math? The Cartesian coordinate grid, named after René Descartes from France. And the myth is that as he was sick in bed, maybe on his deathbed, but I don't think so, but as he was sick in bed, he was looking up at the ceiling at tiles kind of like this, but of actual squares, and he was thinking about maybe a fly or some other piece of detritus on there and how he could locate the fly on that grid by how many squares over it was and how many squares up it was from a corner. Or not up, but this axis and this axis. And that's the legend about how he came up with a Cartesian coordinate grid. We call this axis the y, and this one the x. Okay, and so I'm glad you know that already. I'm not surprised you know it, but I'm glad that you know it because these are the components of projectile motion, are, as our objective says, the x and y components of projectile motion. If you had to guess at this point, which of projectile motion, I've drawn a shape of a, yeah, okay. Mathematically, we call it a parabola. And if I throw something, I'm going to find something unbreakable. Like Justice. Yeah, but I'll just hoist Justice and throw him, yeet him across the room. I want something that is more or less unbreakable, but also isn't going to hurt anything if it hits it. I got my two little skulls from Dia de los Muertos. What are these called? Sugar skulls. Cabeza de azúcar. I don't know. But you can see, hopefully on the camera too, I'm going to throw it carefully over there because that's where I keep my breakable stuff. Woo! Thanks, breakable stuff. I'm going to try to do it a little bit higher. There you go. That didn't quite work. I think on the picture-in-picture you can see it. But when you throw something, and you know this instinctually, when you throw something, it follows this parabolic arc. At any given point on the parabolic arc, let's say this is the path it is following, or will follow. This is where it is right now. At any point here, it has an x component of its motion and a y component of its motion. Actually, at this point, these are wait. At this point, if it's going up right here, we're going to say I'm throwing it instead this way. Then it has a y component of its velocity. These arrows, in this case, are velocity vectors. Remember we talked about vectors in the last chapter. What's a vector?
Direction.
It has a direction. And we diagram vectors. We diagram vectors as an arrow, the length of which is its magnitude, how strong it is. So if I threw it a lot harder, we would draw a longer arrow. That's the magnitude, how fast it's going. In the case of velocity, how fast it's going. What does the direction of the arrow indicate? The direction of the vector, yeah. So this actual motion, I'm going to draw in green here, the actual velocity of it at that point. So we're doing this. Pretend I've got my cabeza de azúcar, and right, this is just like, here's your boy. This is my green hair and my glasses, and here's Tatum with her horse necklace. And I have thrown the cabeza de azúcar, and it's at this point in its path, okay? Yeah? So it's a little bit mirror imaged because I have drawn it that way. But just that exact thing we did, at this point in its path, its velocity, its actual velocity, is this green arrow. But that green arrow, I'm going to get this back to the correct length, that green arrow, its actual velocity, is composed of an x velocity, which is its horizontal motion, and a y velocity. And this is not just semantics and it's not just math. In reality, it has both an x and a y component of its motion, a horizontal and a vertical component of its motion. And the resultant, we call this arrow here, I should do it in green. We call this arrow the resultant. What do you think the root word of resultant is? The result, yeah. Well, basically what we're saying is that when we add together these components, these black ones are components. I've been calling them x and y components, but they are components. What's the word component mean? You should probably be writing some of this down, Justice, I would think. Yeah, it's part of a compound, sure. It's a part of something. So these components of the motion. The actual observable motion is this result, the resultant, but it's made up of these components.
Okay, so your x and y component added together equals the resultant velocity.
Exactly. The x and the y components added together result in, or add to, the resultant velocity. But be careful because it's not arithmetically added. That is, if this vector is 1 and this one is 1, you don't add them together 1 plus 1 equals 2. You add them together geometrically. And in this case, that would be 1 times the square root of angle theta here. Not square root, I'm sorry, ridiculous. The x times the cosine of angle theta, or the y times the sine of angle theta. Have you heard of those words before, cosine and sine? Okay, you're both familiar to some degree with trigonometry. You've done trigonometric identities? Okay, good, perfect. I'm really glad to hear that too. Once again, not surprised, but I am happy. So these components of this motion can be added together geometrically to get the resultant velocity. Let's use something a little bit less complicated than projectile motion first. The one example in your book is that if we have, I'm going to use a bird even though your book used a plane. If we have a kite, like Kesslin kite, we have a kite. This is not the kite of the wind. This is a kite like the bird, a kite, which is it's kind of like a hawk, I think. It's a predatory bird. It's a raptor of some kind. And the kite is flying under its own power at 3 meters per second, but there's a 1 meter per second tailwind directly abaft. It's right behind it. The wind's coming from right behind it, pushing it forward. What is the resultant velocity?
4 meters.
Yeah, these you do just arithmetically add because they're in the exact same direction. What if now we have, I'm going to try, this is actually a pretty good, if I do say so myself, drawing of a kite. I'm going to try to do another one that's pretty good. Not quite as good. Once again, flying at 3 meters per second, but now there's a headwind of 1 meter per second.
2 meters per second.
Yeah, we subtract 2 meters per second. So if they're directly in line, we add vectors. Please write this down. Directly in line, we add directly parallel vectors. And we subtract, arithmetically, no, it isn't perpendicular. It's we have to do geometry for perpendicular. We add directly parallel vectors and we subtract opposite parallel vectors. Those are easy. This one is easy. This one is easy. What becomes a little bit complicated is if we have either this is the resultant, it has both a y and an x component, or we have the x and y components and we need them to add together to create the resultant, where if there's an angle here of theta. You've seen some variable angle represented as theta before, correct? Just like we generally use the variable x to indicate a linear quantity that we don't know, we use the variable theta to indicate an angular quantity that we don't know.
So would you take your
Resultant.
yes, resultant minus your y component against
We have to do trigonometry about it because it depends on this angle. And that's where the trigonometry comes in. So what you would do, let's say we're adding together an x and a y component. So what we want to do, let's call this vector addition, which this is going to have to be pretty fast. And we will go over this in more detail in the next chapter because, and this is a little side note, but all of this applies to any vector quantity, any quantity that has both magnitude and direction, not just velocity. In this chapter, we learn about it with velocity and acceleration. Both of them are vector quantities. And in the next chapter, we do it again with force, which is another vector quantity. We'll do more of it. We'll get the basics now, and then we'll go more in depth with it when we do force vectors. So let's say we have, trying to think of a good problem here. Let's say instead of, we got our kite again, Kesslin kite. We got our kite again, and instead of, it's still going 3 meters per second, we're going to call this, we can, and one nice thing about physics is we can pretty much make up where our origin is. 3 meters per second in the horizontal, we're going to call this the x component of motion, okay? And instead of the wind being right aft, it's not coming from right behind it, it is perpendicular. Let's use the case of perpendicular. So the wind is coming from this direction, and it's 1 meter per second now. So we need to add together 3 meters per second in the x and 1 meter per second in the y. That would be if they're in the same, if they're parallel, we can just add them together like that, but we can't do it like this. So we need to use, for this particular case, we want to find the resultant, which we're trying to find. We know that the velocity, I should have drawn this probably on its little center of mass here, sorry. It doesn't really matter, but I'm going to draw it again on the little center of mass, which we'll learn about in chapter 10, I think. But we're going to add these two things together. 3 meters per second, we could say east or horizontal, and 1 meter per second, we'll call this north. They're at right angles is the point. Okay, so for this particular one, your book tells you the rhombus method. There are really 3 ways to solve, to resolve, we call it. The verb we do is we call it resolving vectors when we add them together with trigonometry or with the rhombus method or with the tail to tip method. There are 3 different ways to do it. The most basic and the way that your book kind of teaches, I'm going to do this, is that we redraw the thing to scale, like we have to use a ruler and a protractor. We redraw it to scale. So I'm going to have each meter per second of my vector is going to be represented by, let's say, you can do 1 centimeter, but that's only going to be 1 centimeter would only be 3 centimeters. So let's say we're doing 10 centimeters each so that I can draw a 30 centimeter line here. So what we do is we draw a 30 centimeter line. I've just scaled it up by a factor of 10 so you can see it. On your paper, you would do 3 centimeters probably. And a 10 centimeter line in the y-axis. We want to make sure that the angle between them is what? 90, because it's a perpendicular. So all we do, I'm going to indicate that with this little perpendicular sign. All we do is measure. So you can see here's my resultant is the hypotenuse of this triangle. The hypotenuse of this triangle. This is going to be my angle theta. The reason your book uses the rhombus method is because what we've just found here is actually like the opposite of the direction it's actually going to go. This diagonal of this rhombus is actually, like if we were to imagine this kite in real life, it's obviously going to be going a little bit like that. Do you see that? And so what we can do is we can add either we can add the y component over here, or we can correctly assume that the diagonals are going to be the same length, just opposite in direction. Either way is fine. This is called the rhombus method because this is a rectangle, but you know a rectangle is a special case of a rhombus, right? Like if this were any angle other than 90, it wouldn't be a rectangle, it would have sloping sides. Anyway, all we do then for this method is we measure it. I find that it is 31 centimeters, which means 3.1 meters per second. And the angle, I would have to measure this angle with a protractor, which I don't have, so I'm just going to guess. That looks to me like about theta equals, or sorry, let's do it this way. Theta is approximately equal to, I'm going to say 18 degrees. I don't actually know, and don't quote me. I don't prefer this method because it takes some finesse. You have to actually be very good at measuring angles. So what we would do instead, what I would do instead, is I would add them together using the Pythagorean theorem. So first of all, if it's at right angles, I'm going to write that out because that just looks like the letter L. At right angles, only, I'm trying to think of a better way to phrase this. It's okay to use only the Pythagorean theorem and some one of the inverse trigonometric identities in order to find the angle. But if it is not at right angles, use trigonometric principles and the Pythagorean theorem.
What principles?
Trigonometric principles. I'm going to rewrite that because I put it, and the Pythagorean theorem. So in this case, what we would do, we know the Pythagorean, since it is at right angles, we use the Pythagorean theorem. A squared plus b squared equals c squared. No news there, right? You're all good with that. Solving for just c, we end up with the square root of a squared plus b squared equals c. C equals, in this case, the square root of, and I like to put it like this because it's how I would put it in my calculator, 1 meter per second squared plus 3 meter per second squared. All that raised to the 1/2 power. The raising it to the 1/2 power is the same as taking the square root. You remember that? That's a question. Do you remember that? To me, that's an easier way of typing in your calculator because all you have to type in is 1 squared, or 1 times 1, plus 3 times 3, press enter, and then raise to the to the 1/2 power, not negative 1/2. And that gives you c, which in this case should be 3.1 meters per second. That's how we find the what of the vector. What's this found? It's the length of this arrow, which is the, yeah, it is the hypotenuse, but of the vector, remember a vector has two quantities, magnitude and direction. We have found the magnitude. To find the direction, what we do is we take any of these inverse identities. So we would put in, let's say, we could use any of them because we know all the sides. This side is 3, this side is 1, this side is 3.1. So we just pick any of them, and then we put them in as, so sine, let's do sine. Sine to the negative first of what's sine? Remember this? Some old hippie caught another hippie tripping on acid. Do you remember this? You don't know this?
Sine is just the one.
You do know this. SOHCAHTOA? Well, sine, what this is, maybe Mr. Snelly does not like this mnemonic, and everyone else who has come into physics has known this, but that's okay. So it tells us that sine is equal to opposite over hypotenuse regarding angle theta. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. We're talking about this angle theta, so let's use sine, which will have the opposite, which is 1, over the hypotenuse, which is 3.1. So we're going to put into our calculator sine to the inverse sine of 1 over 3.1 will give us theta. In this case, theta is, you guys have a pretty good calculator. So what you type in your calculator is second sine, which gives you sine negative 1, and then it'll come up with parentheses. You put in 1 divided by 3.1, press enter, and it is?
0.32845.
What? No, you have it in radians. I know you do because it should be. I said about 18, and I'm not that wrong. I would be surprised if it wasn't between 15 and 25, but let's see what it is. In degrees, please. Are you going to do it? Just, this class is not about how to use a calculator, but just go to mode, switch it from radian on the third one to degree, press enter, clear it out. Booyah! I don't ever say booyah, but it is 18.8 degrees, which actually being rounded would be 19, but I was pretty close. 18.8 degrees. I am a walking slide rule. Anyway, so I know this is kind of fast, but what we're trying to find when we resolve vectors, when we're adding vectors together, is the magnitude and the direction of the resultant. When they're at right angles, we can use just the Pythagorean theorem to find the magnitude, and we use the inverse sign, or sine to the negative first power, or any of the trigonometric inverses to find the angle, to find the direction. And this part is true even if you're not. But let's use one that's a little bit different. You're right. Let's do another problem where they're not at right angles. Give me another example of something that might... Football. Yeah, football. Last night, me and Asher watched the Eagles versus the Vikings, and let's say eagle, which is this color. This is an eagle. Is flying, I think that's romantic, is flying at, if they're running, I would say about 5.3 meters per second. When? Where's my purple? Uh-oh. The Viking will have to be yellow, and this is going to be more or less invisible on the screen. When a Viking comes out of nowhere and tackles him, and we're adding his velocity, we really should do this as a momentum problem, but just for the sake of this, we'll assume there's no friction or anything. We're going to add his velocity, which is, let's call this 6.1 meters per second, at an angle theta of 20 degrees. We're looking down 20 degrees. We want to find the resultant. What is his final velocity? I'm going to do that in black. So what you can tell conceptually that if he's running this way, we'll call this east, and he gets smoked at 20 degrees north of east, and smoke here being used colloquially, he's getting tackled, his resultant velocity is going to be something like this. You can see that, right? If we even draw the other sides of the rhombus, I drew that a little bit cattywampus. There we go. His velocity is going to be like that. We can tell that conceptually, right? Like, you can imagine looking down from above, if Justice the Eagle is running along and Carter tackles him, their velocity will combine, and they'll be going at a combination, a resolution, a vector that is the combined of both of them. So here's what we do, and this is we're going to go through this very quick, but what we do is we break, here I'm going to write down the steps as we go along. I hope you were done with all this. I should have left the label. Vector addition. 1, break both vectors that we're going to add. I'm going to put both or all, because you can do this with lots. I mean, he could be getting tackled by 6 Vikings at once, you know? So break both or all vectors into x and y components. That's step 1. How do we do that? Well, snap them. Yeah. So if we're trying to find, let's think just about the triangle of, well, it's not, you'll find pretty soon it's not a triangle. This is Justice's, the Eagles. I'm using you as an Eagle, Justice, because I asked Asher which team he wanted to win, and he said the Eagles. So that's the good team. These are the good guys. 5.3 meters per second, pure east. What's the x component? It's just 5.3 meters per second. What's the y component? 0. None, because this one vector, this vector all by itself, is just in the x. The other one we have is this one, 6.1 meters per second, at an angle of 20 degrees. What's the x component of this one? Well, we don't know yet, but it's going to be this line. And what's the y component? I'm sorry, it's going to be this line. And the y component is going to be this line, right? So this one only has an x because it's just purely in the horizontal. This one has an x and a y because it has a vertical component as well. So far, so good. Are you with me? Break them both into x and y. We're adding these two things together to get the resultant. Okay, so this one's x component equals 5.3 meters per 0. This one's x component equals, well, it's 6.1 meters per second times, if we want to find the x component, which trigonometric identity are we going to use? Try again. So remember, some old hippie caught another hippie tripping on acid. We're trying to find x. We're going to use cosine. Cosine of 20 degrees. And for the y, we're going to use 6.1 meters per second times.
Cosine.
Nope, for the y. This is angle theta here.
Syntax.
Sine of 20 degrees. Let's call this one x1 and y1. Let's call this one x2 and y2. I like those abbreviations because they help keep us straight. Type it in your calculator. 6.1 cosine 20. 5.7 meters per second. 6.1 sine of 20. 2.0? 2.0 meters per second. Good. Now, next step, add x's and add y's. So the sum of the x, you know what this symbol means? We've seen this before. It's capital Greek sigma. I hope you've seen it before. And it means sum of. So sum of the x, we just add them up. What was the x component of 1? What was the x component of our first vector? 5.3 meters per second. What's the x component of the second vector? 5.7 meters per second. The sum of the x is 11 meters per second. For sum of the y, we have, this one should be easy, 0 plus 2.0 meters per second. What's the sum of the y? 2.0 meters per second. Now, step 3 is build new resultant triangle. So now we put these together, and I really like, I put build here because I really like it to be drawn. I really like it to be drawn. Our x component, and try to draw it to scale, should be 11 units long, and our y component should be 2 units long, and we're trying to find this resultant r. Now from here, the nice thing is, this is always going to be a what kind of triangle? A right triangle. Good. So our resultant equals a squared plus b squared equals c squared. So it's going to equal the square root of 11 meters per second squared plus 2 meters per second squared. If I were typing this on my calculator, I would type it like this. No radicand. This whole thing raised to the 1/2. Give me the r real quick, Justice. I know the bell rung. So 11 squared is 121 plus 4 is 125. What's the square root of 125? Type it in. 125 raised to the 1/2 power. 11.18. 11.18 meters per second is our resultant velocity. And then to find the angle, we would do the same thing we did before. Let's just do, since we have these two, let's do inverse tangent of 2 over 11. Theta equals tangent of 2 over 11 equals 10.3 degrees. That was quick and dirty of how to add vectors, but that should get you through the stuff on the chapter review. We will do more of this in the next unit. Have a great day.